Hi, hello. Myself, Sridhar KM, Assistant Professor of Physics, Government First Aid College, Kolar. Now I am explaining a topic in solid state physics, which is X-rays. X-rays were discovered in the year 1895 by Rontgen, and the discovery was accidental. And these X-rays are a part of electromagnetic radiations having wavelengths in the range 0.01 to 100 nanometer. And these X-rays travel with the speed of light in the form of straight lines. And these X-rays are produced when fast-moving electrons strike a higher atomic weight target. When X-rays incident on a target with larger atomic number with large kinetic energy, and these X-rays are produced. And in this case, a target such as tungsten is taken in vacuum. In the year 1913, an American scientist, W.D. Coolidge, designed a new type of X-ray tube, which is also known as the Coolidge tube. As shown in this figure, this is the Coolidge tube. And this entire tube is called the Coolidge tube, designed in the year 1913 by an American scientist, W.D. Coolidge. And this Coolidge X-ray tube is evacuated, and this evacuated tube consists of a tungsten filament as shown in the figure here. This is the tungsten filament F, which is a cathode, and we have an anode. We are now studying the production of X-ray. This diagram shows the production of X-ray. It consists of a Coolidge tube designed by Coolidge in the year 1913. This Coolidge tube is evacuated. The evacuated Coolidge tube consists of a filament made of tungsten and an anode, and this filament is a cathode. Now, this target is again a block of tungsten or molybdenum, which is embedded in copper anode. The pressure within the tube is maintained at 10 power minus 4 to 10 power minus 5 millimeter of mercury. That is the pressure maintained in the evacuated Coolidge tube. And this copper embedded over tungsten or molybdenum anode will help to conduct the heat sufficiently to the external water cooling system over here. This copper will act as a conductor to conduct the heat generated. The cathode of the Coolidge tube will emit the electrons by thermionic emission when the filament is heated. So when the filament is heated, this cathode or the filament emits electrons by the thermionic emission. Because of the high potential difference between the cathode and the anode, nearly about 50 kV to 100 kV, because of which the electrons will accelerate towards the anode because of this large potential difference maintained between the cathode and the anode, because of which the electrons gets accelerated and strike the target by giving the kinetic energy of the striking electrons to the target. Now it is possible to achieve the separate control of intensity as well as the quality of X-rays independently in this Coolidge tube. This is the advantage of using the Coolidge tube in the production of X-ray. Because of the usage of Coolidge tube, one can control the quality as well as the intensity of X-rays independently. Now coming to the control of intensity and quality. The intensity of X-ray depends on the number of electrons which strikes the target. And this number is further determined by the temperature of the cathode filament, which is proportional to the heater current. Number of electrons striking the target decides the intensity, and this number of electrons further depends on the temperature of the filament, which further depends on the current flowing through the filament. Hence, by controlling the current, the intensity of X-rays can be controlled. Larger the current, large will be the temperature, and thereby more number of electrons will be released from the filament, and hence the intensity increases. The quality of X-ray is measured in terms of its penetrating power. Larger the penetrating power, larger is the quality of X-ray. And this penetrating power depends on the potential difference between the cathode and anode. Larger the potential difference, more will be the penetrating power, and hence the X-rays are said to be of good quality. So greater the potential difference, larger the speed of striking electrons, in the sense larger will be the kinetic energy of the electrons, and thus more will be the penetrating power of X-rays, and such X-rays is said to have high frequency. High frequency X-ray will have high energy and larger penetrating power, and these X-rays are called hard X-rays. Larger the penetrating power, larger will be the kinetic energy of the incident X-rays, and the frequency is said to be more, and such X-rays are called hard X-rays. Low frequency X-rays will have less energy and lesser penetrating power, and therefore they are called soft X-rays. Right? The high frequency X-rays are produced because of the larger potential difference between cathode and anode, and such X-rays will have high energy and high penetrating power. They are called hard X-rays. Low frequency X-rays are produced when the potential difference between cathode and anode is less, and these X-rays will have less energy and lesser penetrating power, and therefore they are called as the soft X-rays. Some of the high velocity electrons, while penetrating the interior of the atoms of the target material, will knock off the tightly bound electrons in the innermost shells, such as K, L, M, N, etc. KL are the innermost, K is the innermost. When the electrons from the outermost shells jump to fill the vacancy so formed, the energy difference is given out in the form of X-ray of definite wavelength. These wavelengths constitute line spectrum, which is the characteristic of the material of the target. When the incident or the striking electrons will have larger kinetic energy, they penetrate deep into the atom and knock the electron from the innermost orbit of the atom. In order to occupy that innermost vacancy, an electron from the outer orbit will make a transition to the innermost, during which the energy difference will be liberated in the form of X-ray having definite wavelength, and which is the characteristic of the material of the target. Now coming to the origin of a characteristic X-ray. X-ray spectra consists of sharp lines and is characteristic of the material of the target. X-ray spectra will consist of sharp lines, and these sharp lines are the characteristics of the material of the target. Targets made of different materials will have different number of sharp lines placed at different positions. Figure 1 indicates the knocking of an electron from K shell when a high-speed electron is incident on it. So you can see here. This is figure 1. And this is the incident electron. Or the incident electron, which is having a larger velocity or larger kinetic energy, thus penetrating deep into the atom and knocking the electron from the innermost shell, such as K shell. and here a vacancy is formed. The vacancy so formed will be filled due to the transition of an electron from a higher orbit, and that can be seen in figure number 2. Electron from L orbit is making a transition to the K orbit to fill the vacancy so formed in the previous case. And this energy difference will be liberated in the form of electromagnetic radiation called X-ray, and that we have represented here as K alpha line. K alpha line. And during the transition, we can see here Ek minus El, that will be equal to h nu, the energy of the K shell and the energy of the L shell. Ek represents the energy required to remove an electron from K shell, and El represents the energy required to remove an electron from L shell. Therefore, Ek minus El will give you h nu, or that will be equal to hc by lambda. That will be equal to hc by lambda, where c is the speed of electron, h is Planck's constant, and lambda is the wavelength of radiation emitted. So here you can see in the figure, you can see here KL, Mn, etc. shells with the number n is equal to 1 represents K shell, n is equal to 2 represents L shell, and so on. When an electron make a transition from higher orbits to K orbit or K shell, when an electron make a transition from the higher orbits to K shell, we get K X-rays, K alpha, K beta, K gamma, etc. When an electron make a transition from L to K, we get K alpha. When it make a transition from M to K, we get K beta. When it makes a transition from N to K, we get K gamma. Similarly, when the electrons make a transition from higher orbits to L orbit, we get L X-rays. When the transition is from n is equal to 3 to n is equal to 2, we get L alpha line. When the transition is from n is equal to 4 to n is equal to 2, we get L beta line. When the transition is from n is equal to 5 to n is equal to 2, we get L gamma. Similarly, the transitions from higher orbits to the third orbit will give you the M X-rays, M alpha, M beta, M gamma, and so on. But if the vacancy in K shell is filled by an electron from M shell, the X-ray emitted will be more energetic. When compared to K alpha, K beta is more energetic and K gamma is furthermore energetic.